Okay, thank you everyone, and apologies for anyone who joined at 8:30. Of course, that was just for us to prepare, but thank you for being so prompt. And I would just like to welcome everyone and thank you for joining us for day one of our annual Mayor's Megawatt Challenge Forum. My name is Catherine Wilson. I'm the manager of the Mayor's Megawatt Challenge. And we're a program that have been working with municipalities since 2003 to improve the energy use in their own facilities. So this is our 9th annual forum, and it's our first online forum due to the ongoing COVID-19 situation. So with this new online format, we're thrilled to welcome municipalities from across the country who no longer have the logistical constraints of attending in person. So the overall theme of the 3-day event is practical pathways to net zero carbon buildings. And today we'll be looking at our actionable roadmap to net zero ice rinks. And I'd like to take this opportunity to thank our sponsors, Simcoe Refrigeration and Enbridge Gas, who have been critical to helping us achieve our goals and our municipality's goals. So concerning logistics, if you have any questions, please enter them into the chat box. Depending on the nature of the question, we'll address them live throughout the presentation, or for common questions or really big questions, we'll address them in a Q&A panel session partway through the forum. And with that, let's move on to our agenda for the day. So we have Jarvis, who will give us his opening remarks. We'll go through the pathway to net zero carbon buildings in general, and then we'll take a closer look at our ice rink feasibility study, which is sort of walking through that process. And we have a technical panel discussion looking at high impact measures for ice rinks and the implementation support needed to get these measures implemented. And we will give an overview of the Mayor's Megawatt Challenge. We have a number of folks on the line who aren't familiar with the program, so just to give you an idea of what we're all about. And then the big awards. So leadership and 10% savings awards will be given out to our member municipalities for making big savings last year. And then our closing remarks. So at this point, I'm going to turn things over to Jarvis, the Executive Director of Climate Challenge Network. Welcome, Ian.
Thank you, Catherine, and good morning, everybody, and in particular, a special good morning to the good folks out in the West. This is a really early start for you folks, and we really appreciate you making the effort to join us. Let's take the next slide if we could. I've been asked to set the stage for the 2020 Mayor's Megawatt Challenge Forum, shall we say, during challenging times, and we're always looking for graphics to try to capture the moment in a way that kind of embeds itself in our memories and so on. And we give thanks to the Hamilton Spectator back in March. They came up with this big idea in terms of the current preoccupation and appropriate preoccupation with COVID-19, but the inevitable economic consequences of everything that's happening at the moment that will follow. And we're seeing that already, and we can imagine the kind of budget pressures that will arise thereafter. But the big wave coming to follow all of that of climate change, it's not going away. It's not. I guess we've got the most advanced naming of hurricanes in the Atlantic this year ever. So we can see the impacts of that as well. So the only thing I don't like about this visual is it's not very uplifting. The idea of being hit by one tsunami after another is not exactly an encouraging way for us to tackle our day-to-day tasks. So we've been told many times to never let a good crisis go to waste. And we've got at least 3 crises on our hands at the moment, and we should not let them go to waste. And we're highly optimistic, and I think what you're going to hear over the 3 days of the forum this year is an optimistic view of not letting crises go to waste, and in fact finding a whole range of win-win-wins that 5 years from now, when we can't remember if it was COVID-19 or 17 or 21, and the economy will come back to life because all the fundamentals of the economy are still strong. The climate issue will still be with us, and we believe that we can be way further ahead on the climate change question by tackling things in the way that we're doing now. and especially with the flood of infrastructure money that will be coming out of governments around the world, it's a great chance again to find those win-wins where we can solve 2 and 3 problems all at the same time. So visually, this is how we see the world. Catherine, the next slide, please. And takes us into Climate Challenge Network. I think many of you are familiar with the organization. We established Climate Challenge Network as a nonprofit back in 2019, and it has a very simple mandate, which is to rapidly scale up greenhouse gas emissions reductions in the buildings sector across North America. So it's really simple, and we're focused on having more and more organizations involved and finding more and more practical pathways to help them go deep in reducing emissions associated with their big buildings. So that's why Climate Challenge Network is here. What sets it apart from any other organization that we've been able to find is the idea that there are targets, and targets drive action. And if you're familiar with the work that we're doing in hospitals and schools and commercial office buildings, as well as municipal buildings, it's all around feeding off the benchmarking of the mandatory reporting, which is cropping up more and more places. It's the essential starting point of data. Having rational targets, which we document and publish in white papers, from that deriving the conservation potential and using that to create the business case and the strategic planning for action. So it's a very simple formula. It's been, as Catherine mentioned, we've been at this since 2003, so it's 15 years we've been working towards this. The database is massive, it's powerful, the analytics are strong, and they're helping more and more organizations across the building sector, in particular municipalities, to take action, to take effective action, and to achieve, in many cases, unprecedented levels of energy efficiency across all of our sectors. We have a great affection for the Mayor's Megawatt Challenge because we see municipalities and local communities as absolutely being at the forefront of this. That's where we see the best action, the most thoughtful action. They're the closest to the communities, and that's where we see the real leverage coming from. That gives us the optimism that we will not let this crisis go to waste, and there will be a positive outcome. 5 years from now, I believe we'll be having this forum. We'll be looking back and saying, wow, a lot of stuff was generated at the end of 2020. So my third slide, if we could, please. So picking up on the Mayor's Megawatt Challenge, as Catherine mentioned, we launched it in the city of Mississauga with Mayor McCallion back in 2003, at that time in partnership with Toronto and Region Conservation as part of their Living City initiative. In 2019, conservation authorities, as many of you will know, have their own challenges and issues to deal with their brave new world. So we parted company back in 2019, established Climate Challenge Network, and as I mentioned earlier, it's all about scaling up emissions reductions and finding ways to really move this. We don't believe we got forever to solve the climate crisis, and our interest now is simply taking the building sector and accelerating progress to achieve the kind of potential that we know exists from the data we've got. The core of this, and I know there's a lot of industry players on the line, and welcome to you. This is a big tent. We don't pretend for a moment to have all or even many of the answers or the solutions. What we do know is that collectively we know how to fix this thing, and the idea of Climate Challenge Network is a big tent where all parties can get together, use data to define practical pathways, to move down those pathways, to verify results and leverage that across all organizations. So I'll finish with 4 points, which or the 4 pillars, which you'll see rolling out across all 3 of these sessions for the 2020 forum. This is all data driven. The starting point has to be good, reliable data that can be processed and analyzed to determine savings potential, identify high potential buildings, because we can't tackle all buildings. We want to go after the ones with the biggest savings potential, and drive continuous improvement. So it's all about the data. It's evidence-based, looking at best practices. So we learn best practices by seeing what actually happens in your buildings. So we take the data, we find where the big improvements are being made, we find the most efficient buildings, and we work with you to uncover what makes them special. We believe totally in networking. When one of the loves we have, for example, of working with Simcoe is it's not just moving forward on arenas, it's we have shared values, and it's good working with people that have similar principles to yours. It's more fun simply working that way. And recognition is everything. Love the fact that we've got our leadership award at the end of today, recognizing the municipalities that really are leading by example and making the big difference. So if I may, I wish you well with today and with the following 2 sessions. This work is important. And while I plan to talk to you again next year, 5 years from now, we will look back on this as the magic moment where we seized the opportunity. We did not let the crisis go to waste. And we really made big headway on the climate change agenda, which in our view continues to be the most pressing, the existential one that's facing all of us. So my best wishes for an exceptionally good day today.
Thank you so much, Ian. That was great, giving us a lot to think about. Definitely. Okay, so that's the perfect segue into why are we doing all this? So with the pending climate crisis, municipalities across the country are declaring climate emergencies. And with these declarations are very aggressive greenhouse gas emission reduction targets. And like I said, some very aggressive. They range from 50% reduction by 2050 to net zero emissions across all municipal buildings by 2030. So we realized there's an urgent need to collectively figure out practical ways to reach these really ambitious goals. And our member municipalities identified this as a priority for 2020, and we responded in the program. So what does this look like? So the roadmap, many of you have seen this before, but for some of you, you have not. It follows a systematic process to identify 4 areas of an integrated solution. So first, we start with energy efficiency, and that's really to improve operations and equipment efficiency. There's a lot of savings to be had in operations, so this is a really strong area to focus on first. And that in conjunction with heat recovery, to use as much of the waste heat as possible and put it back into the building. And this is critical in ice rinks because there's such that high heat load. And energy efficiency and heat recovery really go hand in hand as the 2 major components to reduce the demand of the building to as low as possible. And then attention should be turned to renewables and integrating renewables to cover that remaining demand, and then leaving purchase credits and other offsets as sort of the last resort. So the interesting piece is the zero over time approach. So it's very challenging, of course, to get an entire portfolio of buildings to net zero all at once. So the zero over time approach, and this was introduced at our forum last year by Rocky Mountain Institute. We had Matt Youngcliffe coming to present on that, and that fit right in with our ideas. So really, zero over time approach requires timing the steps towards net zero with planned capital renewal, equipment replacement, and implementing energy efficiency. So getting the entire municipal portfolio of buildings to net zero emissions can be achievable and financially feasible by aligning the planned renewal and equipment replacement with the end vision through a long-term plan. So using a staged approach and leveraging the replacement of life cycle of existing equipment, the assets will be replaced towards the net zero vision instead of replacing like for like. So for net zero to make sense, one needs to consider the total life cycle costs, including operations and maintenance, and not just the simple payback. So having that end vision is really, really important. So this table sort of outlines everything that I was talking about there in the 4 steps of energy efficiency, heat recovery, renewables, and credits. I won't read all of it off, but of course, targets are really important. So having a reliable estimation of the potential in every building, and operational excellence, as I mentioned, is really important. So consistent and well-informed decision making every day. Then energy retrofits, of course, are a key in that as well. And then with heat recovery, we'll get into that quite a bit of detail later on, because that in the ice rinks specifically, it's a really important step towards net zero because there is so much heat there. And then renewables, we'll take a look at that, some of the considerations for geothermal and solar PV are the two main ones that we'll cover. And we won't really get into the purchase credits because that's sort of the last resort. So that was sort of a look at the process that could be applied to any building, but really where do we want to start? So we decided collectively as a group that ice rinks would be a great place to start for many reasons. For one, 20 to 30% of a municipality's energy usage of the whole portfolio is in ice rinks. So they're a really great opportunity and a priority building type for many municipalities. So large municipalities have many rinks. Even the very small municipalities have at least one. And in those very small communities, rinks are really the hub of the communities and a really great place for the municipality to showcase their net zero efforts. Also, there's over 5,000 municipal ice rinks across Canada. So there's a really great opportunity to scale up and engage municipalities across the country to start down the net zero path. And not just for ice rinks, but for other building types as well. So this is the sort of an overview of the pilot where we'll be working through those 4 steps or the 4 strategies to get to net zero. I won't get too much into the details of this, but the participating rinks will receive a customized solution for their participating rink, including life cycle financial analysis. And what will be more interesting to everyone is the standard design that can be applicable to any ice rink. So some generic considerations that could be used and scaled to other ice rink facilities for the participating municipalities, but also for the others that aren't participating in the pilot. And then support for implementation is key. So having the measures is one thing, but actually getting them implemented is another. So we'll be working collectively with other municipal stakeholders to develop solutions for implementation. And that can again be applied to other ice rinks and other building types as well. So this is sort of an early view of what the customized solution would look like. We'd be including life cycle costing, and a list of prioritized measures with the sequencing of when these would happen. Planning the timing with the planned capital improvements or equipment replacements. So that's sort of an early idea of what the end vision would look like for the participating ice rinks. Okay, I will now turn it over to Jillian to give us an overview of who's participating in the pilot.
Thanks, Catherine. So as you can tell, this is a pretty big endeavor and it's certainly a group effort. We've been fortunate to have a technical committee that's made up of some of the leading lights in ice rinks, and they're volunteering their time to lend their expertise to help shape the pilot and develop the measures. So they're working with us to identify and work through the high impact conservation measures, as well as participate in the integrated design meetings for each individual rink. So working on the archetypal rink that is available for anyone to look at, that will be applicable to any rink, and then working on the individual rinks. We have 8 participating municipalities with 9 rinks, and in addition are supported by our funders. We have FCM funding we've applied for. Simcoe Refrigeration, as mentioned, has been a most generous supporter. We have an application in with the University of Toronto for a grad student, Jamie Fine, who is with us today, who will be speaking to renewables, and he's contributing additional modeling, tool development, and his renewable expertise. RDH Building Science is doing the modeling, the building modeling for us. And Climate Challenge Network is providing the project management and the technical expertise. So once again, this is a collective effort. We certainly couldn't do it alone, but we find in general the collective effort is the best approach for developing the optimum design. Now, integrated design is quite common in new buildings, but we use it on an ongoing basis with existing buildings. The idea here is to bring together all of the players who would have a stake in the building, from operators to modeling engineers, facility managers, asset managers, building system experts, putting them all in the room with the building data and the performance data, and taking a look at what is the best solution for the rink, both for our archetypal rink and for the individual rinks of the participants. This will ensure that all of the eventualities and possibilities and permutations are considered. So you're not leaving out operations, which is a big piece of the pie, always, because that's an experience of many people where you build a building and then realize that it doesn't operate the way you thought it would. So this is to manage that piece of it. So that's an integral part of what we're doing. Next slide, please, Catherine. The other is the outcome. So for us, we've called this the low carbon or no carbon design brief. This is the end point for the facility, the concept, the detailed list of what's the individual systems and equipments, what will the end point be for them. It'll be modeled to reach the least possible carbon emissions for all of these systems. It will include, as Catherine has mentioned, the budget costing, so incentives, energy and emission reductions, those will all be included. This will allow you to respond for planned or unexpected trigger events. In discussing this with municipalities, one of the lost opportunities is when you have an unexpected failed boiler, say, and that is your trigger event, your opportunity to really do something different, to take the low carbon option. If you know in advance what you're going to be putting into this building, that allows you to quickly respond and to make choices that lead to lower carbon options. This will have what you need to make the business case internally and externally, specifications generally, so that you have a sense of what you would purchase, or what would your solution be, and it integrates into your long-term capital plan for each of these pieces of equipment, so you know what things are up for renewal when. So it fits in with that long-term plan that merges with asset management. And it provides opportunities to improve the operations of the building on an ongoing basis. So this is our low carbon design brief. So getting started on this path, as Frank will speak to later, we have done most of the site visits for the ice rinks so far. And as always, one of our big findings is getting organized. It takes a lot longer to get organized, and our recommendation is that people do this now. No matter where you are, it always benefits to start looking at your performance and to start getting organized around documentation. So data, start collecting your monthly data if you have that, putting into a format where you can track. Many of you do this in expert fashion. Interval data if available, and submitting high energy using equipment and systems. How are your refrigeration systems doing? When are they running? These can give you very quick wins in terms of operational efficiency if you address that now. In terms of energy management software, essential for tracking performance of facilities. And for those of you who couldn't attend, on September 22nd this year, we had a webinar where Adam McMullen from the city of Barrie had a great presentation on how he uses his energy management software to report and engage his facility. So this is a key step to start getting buy-in on this project and on these efforts. So we highly recommend that. Targets and savings potential. Start now to know how good your facility can be. What is your end point? We will be Catherine will delve into this a little later with the MMC methodology for benchmarking and targets in relation to other similar buildings, so you'll know how you do in comparison with others. This will give you a target to strive for, but also the potential energy savings along the way, that you can achieve along the way. Documentation, collecting your key drawings now. We find universally that drawings are not available or in a dusty closet somewhere, not necessarily electronic. So now's a great time to collect those, any previous energy audits that have been done, and building condition assessments as well. And if your facility has a BAS system, full building or just the refrigeration systems, as many Simcoe systems do, now's the time to start downloading trends and understand how your systems are running. So two data we like to draw upon. One of our technical experts, Les Quinton from the town of Black Diamond, generously let us use his fabulous slides that really show the benefit of tracking data. This is his refrigeration runtime per hour of paid ice. So how long his refrigeration systems run for each paid hour where he's got things scheduled for the town. And this is a fascinating, as you can see, his concerted, dogged efforts to reduce energy over the years in a very straightforward, simple chart, but really useful for him because he can show that he's making good progress, and he can make the business case for more energy improvements because he's saved so much energy so far. Next. This is another great one showing his total water consumption. Pretty straightforward. It's just full total water being used. And despite adding another pad, as you can see in about 2010, he's still reducing water overall for his municipality. So great opportunities to measure what you do. Back again to, this is some of the key drawings. This is an ideal checklist that we developed for when we are going around to the site for the things that we're looking for and collecting, but there's certainly no harm getting this all organized now. Now's the time to start hunting them down, certainly for you in your building. I won't go through them all, but this is all available. As I mentioned to someone in the chat, all of this will be available on our website, this presentation. We can put this up for you. Next, please, Catherine. These are key trends, what we're looking at, and these are critical to understand how the equipment's running, what we can do to make changes and operational improvements. As Frank will speak to later, this is key around getting to optimal conditions within the rink. And finally, another interesting thing we've been learning along the way is that not all building condition assessments are the same. Getting building condition assessments in a format that will inform your long-term project and capital plan is key. You'll want to be able to pinpoint exactly in what year equipment should be replaced and in what sequence. You can see here we've circled the big capital improvements for ice rinks. And this is going to be the foundation for your trigger event map or your trigger event plan, where you know when the opportunities are to make low or zero carbon options. And that's kind of your slow and steady process rather than a like for like replacement. Okay. Thanks, Catherine.
Great. Thanks so much, Jillian. I think that was really helpful for people to see how getting organized at the beginning is going to be critical to achieving the goals at the end and having a long-term plan. Like we talked about with the low carbon design brief, having that end vision and getting organized so you know what you need to do along the way, and aligning that with the asset management plan and all of that. I think it's going to be really helpful for people to really see where they're going and the little steps they can take now to get there. So I think that was great. So we're now going to turn it over to our technical team, who's going to give us an overview of some of the high impact measures that they found so far in the ice rinks. And for one where we don't have a lot of analysis done, what the plan is going to be to really uncover these high impact measures. So we have with us Frank Camilleri, Benoit Rodier, and Jamie Fine, and I will turn it over to you guys to introduce yourselves, and then we can dive into some of the measures.
Great, thanks, Catherine. I'm Frank Camilleri, and I lead the technical support for Climate Challenge Network, working very closely with the technical panel that Jolene highlighted and Catherine highlighted.
And Benoit?
Sorry, we got you on mute there. Sorry, Benoit, sorry.
Sorry about that. Some technical issue as usual. I'm Benoit Razier from Simcoe Federation. I've been working with Simcoe for 20 years. I've been involved with this group. It's been very, very interesting. I'll be here today to support Frank and mainly answer some of the technical questions that that attendees will be going through the chat box. Thank you.
Thanks, Benoit.
Hello, everybody. My name's Jamie Fine. I am a postdoctoral fellow at the University of Toronto. I specialize in analyzing energy systems and developing energy models for more complex energy systems like those found in ice rinks that we're looking at now.
Awesome. Okay. Thank you, everyone. And just a reminder, if you do have any technical questions, Benoit is available to answer them in the chat box. If there are multiple questions or something that we think would require a further discussion, we have set aside a Q&A session at the end of this where your question will be addressed. And if there's a great number of questions like we did have back in our heat recovery webinar in April, we'll circulate a question and answer document along with the slide deck and the forum proceedings after. So be rest assured all of your questions will be answered at some point, either the chat box, the Q&A session, or the takeaway document. Okay, so let's move on here.
Great, thank you, Catherine. So I'd like to talk a little bit about, just to get everyone on the same page regarding ice rinks and some typical energy use within those types of facilities. So as you can see over here, again, this is just a typical ice rink, and you'll see that the refrigeration load is the largest load within a rink, and no surprises there. And HVAC is sort of the next biggest one, and lighting is a smaller portion of that. But if we can go to the next slide, what I'm trying to show with this is to demonstrate that on the refrigeration side, there are lots of opportunities to make that process run more efficiently. As you can see there's a discussion about floating head pressure, which we'll get into a little bit more, low E ceilings, VFDs on the brine pumps. Again, that's just strictly making the refrigeration, optimizing the refrigeration function and process there. If we can go on to the next slide. And this is the added component which we'll be focusing a lot on for the ice rink initiative, because we are trying to reduce, and our main target is reducing carbon, so trying to remove the need for gas heating. And as you can see, the refrigeration actually goes up a little bit more than it did, say, perhaps in the previous slide, because it's using a little bit more energy, but you can see that's more than offset by the HVAC savings that arises from using that heat recovered energy. And you can see that the HVAC there is about 2% there, and that'll vary from building to building, but that's pretty well the only supplemental heating that typically is required if you're able to be very successful with the heat recovery from the refrigeration system. Okay. So Catherine mentioned that, and so did Jillian, we're talking about some high impact measures. So as mentioned on this feasibility study, this initiative, we've already walked seven sites. So and I'm going to share to you some of the findings to date. Again, feel free to ask questions. Again, we're probably about 40% through this, so we have a lot to learn. And but I'd like to share the actual findings to date. And as mentioned before, one of the biggest areas of opportunity will be operational optimization, basically making the best of the equipment that you do have. As that four-step process that Catherine identified beforehand, we're going to try to make the building and the ice rink as efficient as it can be before getting into heat recovery, and then down the step forward through on-site renewables, and then as a last resort, purchasing local tax credits. So again, operational is a big piece of it. We'll touch upon retrofit and equipment replacement, especially as it relates to the whole concept, the whole approach of zero carbon over time. We discussed trigger events, and that's when a lot of that sort of comes to play. Some of the key areas that we will be focusing on, again, just a little bit of feedback from and share with you some of the findings to date regarding lighting, building automation system, what we observed on site, facilities with low ceilings and those without, opportunities for optimizing the refrigeration operation and heat recovery. Again, that'll be a big component there. Dehumidification is a standard feature in rinks, and we'll try to make the, again, we'll talk a little bit about some replacement and retrofit options and even just operational items that can help improve that. Some other items that come to play with respect to the amount of energy that is used in the ice rink. Ice thickness matters, so does the ice temperature that you maintain it throughout the day, depending on the type of activity that goes on there. And ice resurfacing also has a significant impact on the refrigeration load. So we'll talk a little bit about our observations and some of the things that we're seeing there that could help reduce that energy on the refrigeration system. Great. So we'll start off with lighting. Based on the walkthroughs that we've done to date, most facilities are going from fluorescent T8s to LED. And so most of them at this point in time that we've observed, that most of them are going about it where, you know, when a bunch of them fails, they will actually go replace a bunch of them. That can make sense if, I guess, will depend on the specific municipality and I guess their capital funds and operating budgets. But there's a couple of ways of going about it, and one of them is just waiting for a bunch of them to continue to fail, or you can actually take the next step, which is, or a different step, which is group overlapping. So especially, you know, it's not tremendously difficult to change lamps within, you know, normal low ceiling places like change rooms, offices, and things of that nature. But when it comes to the actual ice pad, over the ice pad, that's very challenging. You're going to need a lift. So if you get into a situation where a lot of the existing fluorescent heat is failing, a lot of it is failing, you might want to consider group relamping with similar light levels. And I guess one of the things to highlight is that it's important to also look at the type of LED lamps. There's a lot out there, a type of LED lamps and color and actual intensity that can significantly impact the light levels in the facility. And what we generally have noticed is that typically the light levels with LED replacement have typically increased rather than decreased. So something to keep in mind. We don't want to overlight the place either as well. So make sure that we're taking advantage of providing the amount of lighting that's necessary, but not overdo it. Again, that will consume more energy as well. Some of the other areas that we've been focusing on as well when we walk on site, we've been talking about or looking into the way lighting is actually controlled within the facility. For the most part, a lot of occupancy sensors are being used in change rooms, in washrooms, areas that have variable occupancy throughout the day. And there are meeting rooms, again, that have permits from that vary throughout the day. And so those really work well. Local occupancy sensors in those types of areas really work well. One of the areas that we have sort of mixed observations, if you will, is you know, controlling the lighting within the ice rink itself, the pad. And we have, you know, anywhere from lighting controls just with manually turning them on and off. Some of them have dimming capability, and they kind of vary it, but there are again, a wide range of ways that it can be controlled. But we believe that lighting controls, at least with on and off capability, and even bonus if you have the dimming capability with the ice rink. And I think a lot of that just comes down to that instead of relying on staff to turn them on or turn them off, you know, that it should happen or could happen when it really needs to, around working around the occupancy schedules, the permits that actually happen within the rink itself. And the dimming is an interesting option. We've seen that in a few areas. A lot of that is, if you take advantage of it, you can you can cater the light levels for the type of activity. So when there's maintenance being done on the ice pad itself, typically you want to go as bright as you can, again, so that the work can be done and great visibility in that. But depending on the actual the event itself, you might have different levels of lighting that do that. We've seen that done successfully at a few rinks as well. Okay. Catherine, do you want to go to the next slide? If you so low E ceilings, this has been around for a while. There's been lots of talk about and seen a lot of them installed. What we've seen is in particularly a lot of the older rinks that we've seen, low E ceilings have been installed. Basically, it's the the concept that that ceilings, typical construction materials, can contribute significantly to the refrigeration load. A lot of that has to do with the emissivity of it. So as you can see, so typical things like typical building materials like concrete underneath, those typically will have high emissivities between like 0.8 and 0.95. And again, quite a bit of that radiates back down to the ice and adds to the load. So as much as 30% can actually be portioned to the refrigeration load, can be added to that. Low E ceilings, what we're seeing again is a lot of the older facilities, typically we find them installed, but we're seeing, surprisingly enough, some of the newer facilities just don't have that. Although there are materials in some of those newer facilities that have a lower emissivity than typical construction materials like galvanized steel that has an emissivity of closer to 0.23 or 0.3, while I mean it gets a lot better than typical construction materials. You can do better than that. Aluminum foil or similar types of materials that have low emissivity, could be down to like 0.08. Again, this is an index to give you an indication of how much it absorbs and how much it reflects, and so typically you can get down with aluminum foil quite significantly low emissivity, and just in our research to date, we've been finding that typically it's typical rinks. I mean, obviously it'll be different for each facility depending on the roof construction and the lighting layout. It's between $40,000 and $60,000, and typically has a 5 to 8 year payback with just utility cost savings, not including any carbon offsets or costs of that as well. So again, something still to be familiar with or keep in mind when considering low E ceiling is that you need to kind of work around the light fixtures. And as well, be mindful that typically when you install a low E ceiling, depending on the emissivity of what you currently have, the light levels will increase. So you need to take that into consideration because, and that's where dimming might come in handy, sort of tying that together. But dimming can actually, if you have that capability, might be able to reduce your light levels, or the usage a little bit more by just maintaining existing light levels before you install the low E ceiling. Okay. So building automation systems, this is essential to operate the facilities efficiently. I mean, building automation system is just a key ingredient that's necessary for pretty well all facilities that we come into, but it's in rinks as well. It's extremely important. Based on our site visits, we typically find some sort of controllers that control the actual refrigeration system. Since most of the systems to date have been Simco, we've seen typically when it's Simco that's servicing them, they'll have a building automation system front end that actually helps review and navigate through the refrigeration system, but mainly the controllers themselves actually do the controlling. Again, Simco typically made the use of Delta controls as sort of the front end, but again, the controllers themselves specifically will actually do the controlling of it. As most of them can be accessed remotely, so which is good. If there are any problems, someone can call from wherever their office or a technician can reach out without having to be physically there to see what's actually going on with it. One of the observations is that there are very few that are integrated with the rest of the building. We've only seen, I think, one of the rinks, that one or two tops out of the 7 that we walked to, that has some integration with the rest of the building HVAC system. And it's important because you can integrate that with it and to make use of the available heat that is there. It can exist when you're getting close to that low carbon solution that you can use within the facility. And again, some don't have a building automation system for the rest of the facility. So again, we get this kind of wide range. Again, typically there is something for the refrigeration system, which is great. And you can usually view it through a building automation system front end. But very few are integrated, and there are some that actually don't have a building automation system, period. Everything is just local controls for the facility. On the building automation system front, some of the key things that we do when we see them there is that they can definitely be optimized. And this is where things like scheduling, occupancy, unoccupied operating strategies are typically things that you would do with your building automation system. Also, just optimizing the operation of the equipment, making sure it's in the rest of the facility that it's actually using economizer mode properly, and taking advantage of any heat that could be used within from the refrigeration system within the facility. One of the key items that you've heard repeatedly in this is the value of trend logs in archiving. Again, we were very happy to see that the refrigeration system would typically have trend logs pretty well from the inception of the installation. We've seen them up to as early as 2010, 2011. So it seems, again, on our observations, that trend logs typically exist, but that doesn't mean that all of them will. I think there were a handful that didn't have that capability. And as Jillian mentioned, this is an opportunity to really look and get ready for this and make sure that if there's some opportunities to either sub-meter, if you don't have a building automation, sub-meter some of the bigger loads, but also if you do have the capability, set up the trend logs for your refrigeration system. And if you're fortunate enough to have something for the HVAC side of things as well, set up trend logs for that as well. One of the key things that we're always, or what typically surprises us and the operators is, during our site visits, we talk a lot about, asking the operators how they operate the facility. And then it's when you show the trend logs that you see that it doesn't often operate the way one thinks. And again, that's the value of the trend logs. They don't lie. They tell you actually how it operates. So it's just good information, and it's really essential for making the building as efficient as it can be. Okay, so we'll focus again. The refrigeration load is the biggest energy user of the facility. Some of the typical measures that we've seen here, floating head pressure control is more of an operational thing. There are variable VFDs on compressors and cooling tower fans. It's very common to see them on the cooling tower, especially if the equipment is fairly new, but that can easily be retrofitted. Staging and optimization of that process is an area that we're focusing on by analyzing the trend logs. Adding VFDs, again, not just to compressors, but also to brine pumps. The refrigerant choice has come up a few times, and the impacts on the environment and building efficiency is something, though, because we'll explore a lot more in the future. We're not quite there yet within the initiative, and it deserves quite a bit of attention, and deserves a sort of separate webinar, if you will, on something like that, on something of that nature. If we can go to the next slide. So just a little bit more about the measures we're describing. So floating head pressure, basically, that's the concept of just varying the head pressure based on the outdoor conditions. So typically, the ice rinks will be designed for peak design, and it'll be based on outside air temperatures that are pretty hot outside. But in the middle of winter, there's no need to have to control to that higher head pressure because the temperature outside is a lot colder. So again, varying that, making it a floating head pressure is really good. So we'll be looking at trend logs for actually how it actually works. One thing about floating head pressure that you need to keep in mind that if there is heat recovery being done within the facility, then this higher head pressure floating strategy isn't quite as useful and as common, because you need the high pressures to actually get the heat that you need to be used in the facility. So VFDs, again, we talked about it. We're looking into the viability of VFDs on compressors. And we're seeing more and more, though, commonly done is VFDs on brine pumps. We've seen that on condenser pumps as well as in cooling tower fans. And again, trend logs are going to be very helpful to help us understand the opportunity, the potential to save based on their current operation. And again, just because they have VFDs doesn't necessarily mean they're efficient today, right now. That we typically find opportunities for improvement on that. Again, trend logs being the key thing here to try to understand existing facility. We'll also be focusing on how compressors are staged. Again, coming back down to trend logs to understand how it currently operates, and just trying to understand if there are improvements in the way you stage things depending on the loading that is occurring on the compressors themselves. Operation of ice storage. This is one of the more up-to-date systems that we've seen at the archetypal actual facility, where they have ice storage to help deal with the mismatch of heating and refrigeration loads, right? So we can talk a little bit that more at a later time as well. If we can go to the next slide, that'd be great. So again, big topic, heat recovery. This is the big topic, if you will, with respect to getting to low carbon. There's a lot of heat that is rejected from the refrigeration plant to maintain the ice. And normally, again, typically in the past, it would just normally be rejected outside. And again, that doesn't make sense when most of the facility requires heating. Again, this heat can be recovered. There have been applications for a while for doing this, and we'll talk a little bit about each one of them in the next few slides in deck. Talk a little bit about de-superheater. That's been used for quite a bit. That actually is used at the outlet of the compressors, recovers up to about 15% of the rejected heat. And typically this has been used in the past to heat up domestic hot water. And then there's also further heat recovery beyond that can be done before the condenser, before you having to reject it outside. Again, we'll talk a little bit more about that in the next few slides. So, again, there's a lot of heat that is rejected from the refrigeration plant. And, where would the heat be needed? Well, there's a whole bunch of areas. This tries to illustrate to you where the opportunities are to use that heat. So we can see there from the top right, the space heating. We know that there's these ice rinks often operate during the winter. Usually they're actually 8-month facilities, but we do have year-round facilities. There's the water heating, which we're talking about with the de-superheater. That's domestic hot water loads. Snow pit. The snow pit typically requires a bit of heating to melt it. So, as well as spectator heating and underfloor heating. Again, many areas to use the heat. It's a matter of trying to find it in the right form or putting it into the right form that can be used within the facility. Okay, so next slide. So this is an interesting slide trying to show that the red line is the heat that is rejected by the refrigeration system and how that varies throughout the year. And then the blue is the space heating requirement. So you'll see for most of the year that the heat rejection from the refrigeration system is much greater than the heating requirements of the facility. But you can see there, and it'll depend on the facility specifically from into the winter months, kind of like December, January, right through to maybe February. You'll see that the refrigeration heat that's rejected may not be quite sufficient to handle those peak days. And that's where supplemental heat will likely be done. But again, for the most part, the heat rejected by the refrigeration system is more than ample to cover the heat that's required in the in the facility, and most of that heat that we're finding typically is provided by gas-fired boilers. So again, getting to that low carbon solution over time is to try to make use of the heat rejection and minimize the operation of any gas-fired heating. Okay. So heat pumps or heat recovery chillers, we use them. It's been a common practice, more so recently, being getting a lot of attention recently in other markets where we're trying to use them in commercial facilities. They've been used, again, it's different applications, but heat recovery chillers have been used in healthcare facilities for a very long time. And they've also been used here as well, but so they have an interesting concept over here. And we're going to be looking at this a little bit more detail. One of the things is that sort of motivated the use of the heat pump or heat recovery chiller is the fact that the temperatures that are available through the refrigeration system, sort of the condenser side before it actually is rejected to outside, is typically lower temperatures, typically around the 95 degree. It could be as high as like 110 degrees as well, which is okay, but it's usually not sufficient for too many sides. It's fine if you have, say, in-floor radiant heating. So great if you have a new facility and you would like to design for the lower temperatures. Yeah, you would put in-floor radiant heating is a good option. But again, we're dealing a lot with them with existing structures. They don't have a lot of them don't have that feature in them. But with the heat recovery chiller or heat pump, you'll be able to produce higher temperature water, about 160 degrees or so. And this is where it's a bit of a game changer, because this 160 degree water can be used pretty well anywhere within the facilities, or at least a sufficient temperature to be used anywhere in the facility. Usually, again, what we've seen is a lot of the heating is provided by convectors on the perimeter, and typically they're designed for about 160. So this works out really well. Again, that's just usually peak loads, but this heat pump or this heat recovery chiller allows you to make the most of the heat that's recovered from the refrigeration system, makes it usable because of the higher temperature is to be used in the space heating. Again, as that graph showed, with this concept, you can actually use, it can offset most, if not all, of the gas-fired heating in the facility. You can go to the next slide. So Jillian talked about trigger events, as well as Catherine. The trigger events is basically this approach of low carbon over time. Again, very difficult for municipalities to change everything all at once. The premise is that when you have to change equipment because it's either failed or it's at the end of life, those are events, the times that you would actually consider what kind of replacement is necessary to get me closer to that sort of low carbon solution. So things like when a cooling tower needs replaced, boiler being replaced, dehumidifiers, or if there's a ventilation upgrade, these are all trigger events that should be are opportunities to actually rethink what you should replace the equipment with. The days are gone that you just replace like for like. The low carbon vision is what you should be having every time you're looking at this. And we're going to go through a couple of examples. We'll talk about some analysis we've done with a trigger event that actually occurred for boiler replacement, and some of the things we're considering with dehumidifiers at this point in time. Okay, so just talking a little bit more about the heat pump. So this is an actual analysis that was being done for one of the participants. Again, a lot of this was instigated because of a trigger event. Their boiler plant is sort of nearing the end of life, and their capital plan has indicated that this year would be the year that they would like to replace those boilers. And so again, stepping back a little bit, indicating, okay, what should we do to get closer to that vision? Should we replace it with new gas? Could we avoid boilers altogether? Again, a whole bunch of different questions were being asked, and this is what led to this this analysis. And the thinking is that, well, more than likely, again, we'll talk a little bit more about heat recovery and some challenges that you do face. But if you do have the opportunity to recover heat, and again, a heat recovery chiller or heat pump is a good way to go about doing that. What would, having that in play, where does sort of the supplemental heating fit? Are gas boilers still needed? Can we use something else? Anyways, this is just the next few slides. We'll talk a little bit about that. This is just sort of the general concept of the heat pump. So again, heat pumps are available where they actually can convert the heat from lower condenser water temperatures to higher condenser water temperatures. As you can see in the top center, that is the heat pump, and in the bottom sort of right, that equipment there is that equipment over there is basically making use of the actual heat that's available, and that's high temperature heat, water that's available. We go to the next slide. This is a step beyond that. If we add a subcooler, we can actually reduce the temperature after it's been used in some of the heating elements within the facilities. So, for example, if it's being used in the perimeter rads, there's an opportunity it'll come back quite a bit significantly hot too, that could still be used for some other application. And I think the next slide talks a little bit about that. So you can see that having a heat recovered chiller, the heat pump, ammonia heat pump, the first stage of heating, again, we talked about high temperatures. We could be circulating water throughout the facility, good enough to handle, again, radiation, perimeter radiation, as well as, heating coils in the air handling units. And then you can see that just beneath that, after it does come back, you still have the ability to make use of the heat and actually reduce the water temperature even further. And that's where, you can use that for heating up, makeup water, or providing other heat for domestic hot water needs. Okay, next slide. So this is a bit of an analysis that we've done. Again, it will be a little different for each facility. And again, the use of a heat pump will be very specific to the facility. But just initially, just to help address this trigger event and try to understand what is sort of the best approach, given that they're at the stage where they need to replace the equipment because it's at end of life. We performed a little bit of analysis. We said, okay, well, if we have the installation of a heat pump, assuming it's viable, we had some high-level numbers regarding the heat pump. We performed a bit of an analysis on the gas consumption that we felt could be saved within the facility, could be avoided. Again, this is preliminary, fairly high level. The next stage would obviously be more detailed. But also looked into the fact that there's going to be an electrical increase because of the use of the heat pump compressors. But you'll see that utility cost savings with a heat pump would only save about $5,200. So that's kind of right in the middle, bottom in italicized there, about $5,200. So if you just look at utility costs alone, the heat pump isn't extremely attractive financially. It's where you take into consideration the greenhouse gas reduction. And so we looked at the tons of greenhouse gases that would be reduced if they use the heat pump application. And we, again, this whole life cycle cost analysis will take into consideration, at least with this initiative, will take into consideration the cost of that, because again, as Catherine mentioned, you have alternatives. If you don't do anything and the municipality is committed to achieving their low carbon goals, they have a choice. They can actually make changes within their facility. That would be things like heat recovery or on-site renewables, or actually they can actually go and purchase credits. So we're at the preliminary stages. We're using $150 per ton just for now, because we're going to be looking at a life cycle time frame of 20-25 years, as far out as 2050, because that's where most of the goals sort of targets reach their end. And when you take that into consideration, that's when it becomes a little bit more attractive. Again, a different way of looking at things, but for this particular initiative, costs of greenhouse gases is something that's going to be very meaningful. So you can see that that's a factor of 4 times the energy savings. So energy savings alone won't drive this. It's the cost of greenhouse gases that will help drive it. You can see with the cost of greenhouse gases involved, it's about $25,500. And the simple payback, again, this is just more of a simple version. The intent is to do a complete life cycle analysis for the Rink, but at this point in time, just to get an indication with what to do with the boilers, we're in around the 22-year payback. So this is assuming that, you know, they've got to a point where heat pump is something they're going to proceed with. Where does the gas-fired boiler sort of fit in? So because the intent is not to do something if it's not necessary. Why should we replace the gas-fired boilers with gas-fired boilers if they're not needed in the very near future? So that was the analysis with natural gas boilers. If we can go to the next slide, there was some questions about should we be using electric boilers as a backup. Again, electricity is a lot more environmentally friendly, has a lot lower greenhouse gases attached to the production of it. So again, this is the normal thinking that one needs to consider when coming time to replacing anything that's gas fired. We know also in Montreal that this is something that can be typically used, especially how clean their electric heating is. Now, again, one of the biggest problems with this is that although it is clean from a low carbon perspective, it is very costly. It's by a factor of 4 or 5 at the current state of gas prices. Now that will evolve over time, but again, just to get a preliminary analysis, you can see that the estimated cost savings, there really aren't any utility cost savings. There's actually an increase. You can see it there. It's close to $19,000. So again, just converting from natural gas to electricity is quite a bit of a cost implication for the municipality, again, because electricity is a lot more expensive. Again, even when we take into consideration the greenhouse gases, you'll see that the tons of greenhouse gases of using electric versus gas-fired is higher. I mean, I think we showed about 130 tons, and this is 155 tons. And taking all that into consideration, the estimated savings is about, in aggregate, about $4,500. And you can see that the payback is considerably higher. And the reason why a lot of this comes out to this situation, comes out with this result is that the intent is to recover as much heat as you can, that based on that graph that you saw in terms of heating needs of the facility versus the heating that's produced from the refrigeration plant. You see that the vision that this will be just top-up heat. The gas heating and the electric heating will just be top-up heating. So if we go to the next slide. So this is taking into the consideration the whole heat pump and the cost of the boilers themselves. So this is if the client decided to replace them with gas-fired boilers, and you know the payback isn't the greatest, but again, you need to take into consideration the fact that there is a need to that this equipment is at the end of its life. So again, 30.8 years simple payback, not the greatest, but you have to replace these boilers with something because again they're at end of life. You can go to the next slide. So that was the gas fired, the electric fired. So in this specific case, sort of the analysis just shows that that if you're going to replace it with, if you're going to need to replace these gas fired boilers, what option should you be considering? And right now, the economics point to replacing it with a higher efficiency gas fired as opposed to going to electric heating. Again, that will depend on each facility, but I just wanted to show you how the analysis can work out for an example of real life example of what's actually occurring in one of the pilot facilities. Okay, a lot of information there, but it would just, the main points coming out of that is that, you know, in this case here, a trigger event happened, boiler replacement was required, or equipment was at the end of life. What do you need to do? And in that case there, at least right now, the analysis, preliminary analysis shows that you're better off still replacing it with gas-fired boilers. Usually you would want to replace it with higher efficiency ones. Okay, so if we can go to the next slide. Again, something to just keep in mind is that the Rink configuration does matter a lot in terms of the viability of these heat recovery opportunities and the financial viability of it. So you'll see that a lot of this heat recovery opportunities need some space requirements, and we're finding that older refrigeration rooms typically don't have a lot of space. We found a lot of space in newer facilities, quite considerably more. So there might be some kind of space constraints that you have to deal with, and which can make the whole initiative either not doable or very costly. And the access to heating sources based on the location of the refrigeration plant is a sort of a big factor. But what the good thing about this, typically we have found that usually boiler plants are next to the refrigeration plant. So that part is fairly easy. Again, just want to highlight the fact that heat recovery is a complex thing, and it is very custom for the specific rink and how you can access it and the space available for it. So again, just wanted to highlight that focus, even though the focus for low carbon is typically around getting as much heat out as you can, there are constraints you need to be mindful of. Okay. Okay, so we talked about heat recovery. Now, this is, again, another real life trigger event we're experiencing with the pilots, is that there's one of the actual participants that's actually at a point where they need to replace their dehumidifier. It's sort of at end of life. And so these are some of the things that we're considering for that. Again, always looking through the lens, through this trigger event, here's an opportunity to say, okay, what should I replace it with that will ultimately get closer to that sort of low carbon sort of ideal state, if you will. So we talked about 3 different types of measures. The operational measures are retrofit options and replacement options. So we'll go through a little bit of that in the next slide. Jillian, I think, and Catherine as well mentioned the technical panel, and Les Quinton from Town of Black Diamond. Again, we're fortunate to have him as part of the technical panel. He makes use of a lot of this. We're learning a lot from him. He leverages the use of outside air to maintain humidity levels in the rink. For a good part of the time in the cold weathers, you can minimize the energy consumption by trying to take advantage of the low humidity that's available outside. So again, optimization opportunities exist with trying to take advantage of the outside air where it makes sense. It's sort of that trade-off between any heating that would be required. But because ice rinks typically, don't have high temperature, space temperature conditions there, I mean, the strategy can work quite a bit. And we're finding that on site there, humidity set points varied from one rink to the next. We've seen them as low as, I think, close to 40%, but we feel there's an opportunity, to increase that setting. So again, the higher that setting, the lower energy that's required, the reduced energy that's required to dehumidify it. So again, this is the focus on the operational side. Without doing anything, any replacement of equipment, these are the types of things to consider when operating the existing equipment. Next slide there. So these are dehumidification retrofit options. This is when you try not to have to replace the whole piece of equipment, something that we'll be considering for each of the facilities. So different options of dehumidifiers that we've found. One of them is a sort of a mechanical dehumidifier using a typical refrigerants, where it pulls it off, removes the moisture, and then heats it up again. The recommended replacement was an upgrade needed for latest technology. So there's, in that case there, because you're dealing with refrigerant-based technology, the replacement might be one of the only options that you have. Again, we're still in the preliminary stages of this. In the case where there is a gas or electric desiccant dehumidifier, which is the case that with the actual participant. In this case here, there are some options that you can do with retrofit, which could be adding waste heat coil or the removal of gas. Again, the thing is that if you're in this case over here, specifically for the client or this participant, they have to, the existing equipment's at the end of life. But when we find certain sites that have dehumidifiers that have a bit of life left, there might be this option of adding a waste heat coil if it doesn't exist, to again try to recover some of that heat. So if we can go again, that's a bit of a discussion on retrofit options, and then the next stage is talking about different replacement options. So again, if you have the 2 main types that we're seeing, a mechanical dehumidifier and a gas or electric desiccant dehumidifier, very similar options for both. You should be considering electric dehumidifiers as opposed to gas-fired ones. And then if you're fortunate enough, and you should be looking at some reactivation heat recovery opportunities too. That basically is being able to recover the heat that exits the exhaust to use that somewhere else. Basically, the desiccant needs to be heated to make the thermal wheel a lot more effective at reducing the humidity, but instead of that, usually produces higher exhaust air temperature, which can be recovered to provide heating somewhere else in the facility. So again, just when you're considering replacement options, electric should be top of mind. And if there's an opportunity, there are some different options up there to actually recover, putting a waste heat recovery coil before the air is actually exhausted out, so you can use that somewhere within the facility. Okay, so a lot of information with the dehumidifiers, but basically, again, this is just a general concept. How it works is you can also use waste heat recovery from the refrigeration system to provide heat to dehumidify. So again, there's a lot there on the dehumidifier aspect of these rinks. And just again, some things to be mindful of and to consider. And again, we're at the early stages of this at this point in time, but you got some ideas of where our current thinking is with the replacement of chillers or just the operation of these dehumidifiers. Okay. Next slide. So this just talks about that the dehumidification using reactivation. Basically, if you look at the top left corner, that's basically the temperature of the air that you have. That on the exhaust side, that's the product of using using a heated source to make that thermal wheel a lot more effective. But instead of discarding it out, again, trying to recover that, so using recovery coil to make use of that high 135 degrees to see if it can be used elsewhere. Okay. Okay, so next slide. So opportunities here for, again, some operational items that we can focus on, specifically on the ice. So again, ice temperature is a big factor within the pads. Typically, year round, it can be used about, typically we see it -6 degrees Celsius, but you can see there's an opportunity for to actually increase that temperature. There's no need for all events to be operating at -6, depending on the type of activity. So you can see figure skating they like it a little bit softer than, say, for very harsh environments like with hockey, especially competitive hockey. They'd want it a little bit colder again. But again, figure skating, free skating tend to be more amenable to higher temperatures for that. And during unoccupied periods, there's an opportunity to actually let the actual ice temperature float a little bit higher than the set point during the day. Again, this can reduce the refrigeration load materially. So again, opportunities from an operational perspective to improve your efficiency and reduce refrigeration load with the way you manage the ice temperature. Go ahead, next slide. So another area where that in fact impacts the refrigeration load is ice resurfacing. So again, some observations so far is that we've seen most of the ice resurfacing machines are gas-fired, natural gas-fired, and there's one or two of them I think that we saw that were electric. But when considering replacement, electric should be considered. Again, just that vein of low carbon. Again, we need to reduce the amount of gas usage in a facility and go to electrification, where the greenhouse gas is a lot less, especially in Ontario. Water temperature is another big factor that could affect the refrigeration load. So we found ice temperatures used in the resurfacing process. So these ice resurfacing machines, we saw them varying from one facility as low as 120 or 130, as high as 160, 170. So there is an opportunity to reduce that temperature. And so there are systems out there like Real Ice, and we'll be investigating other systems as well, or just even in general, just reducing the temperature if there are ways of doing that while maintaining the ice quality that people expect. So again, if there are opportunities to address and lower the water temperature used in resurfacing, that tend to lead to the result of a reduction in the refrigeration load the ice there. So all while maintaining good ice quality. The goal is to still keep that in mind. That's at the forefront. You need to maintain that quality to provide that continuous surface in a rink. Let's see here. Okay, good. So this is over to Jamie to talk about the renewables piece of it.
All right, thanks, Frank. I don't have quite as much to talk about and not quite as in depth or interesting as Frank was just talking about, but nonetheless, I have a few comments just on the renewable aspects of what we're starting to look into. The first is just looking at solar PV. These are pretty straightforward systems. You're gonna install on the rooftop of the building these solar PV panels. And the whole point of these panels is to generate electricity, which is, it's the common way these panels are used. But the important part, just to remember if you're not familiar, is that when you generate the electricity, at least in Ontario for the most part, you're going to sell that electricity to the grid. So you're not going to go generate it for the most part and use it on site. You're going to have it on top of the building. It's connected to the grid, and you're going to sell it, and that's going to generate. As far as I understand, the most current policy is that you're net metered. So they're going to count the amount of kilowatt hours that you export from your site. They're going to count the amount of kilowatt hours that you're importing to your site, and they're going to find out the difference. And that's going to reduce your electricity bill. And then if you're trying to reach net zero energy, the net difference in these two numbers is going to contribute to figuring out how much energy you consume on site to how much energy you're producing on site. And again, these systems they're pretty standard. There's nothing really special about them from an ice rink perspective. And just to keep in mind that you're not really intending, for the most part, to use this energy on site. You're really planning to export it to the grid. If you do plan to use it on site, you can, but it's going to become more and more expensive. The systems, you're going to have to move over to like DC lighting or something along those lines. They're more complex to start using on site. Or if you wanted to use battery power on site, that you would start charging batteries on site with this equipment, it's just going to become quite expensive. The technology is not really there at this point in time. So for the most part, if you're looking at PV, you're looking just to export it. That's pretty the common approach here with PV. Hugh, the next slide. Yeah, perfect. The next one is solar thermal. So again, we're covering these because these are the typical approaches when you start looking at renewables. Is you're going to look at solar PV or solar thermal. Solar thermal, and if you remember that slide that Frank showed seems like quite some time ago already, there was a slide that showed a demand curve or the heating demand curve and the heating rejection curve, and it showed that depending on the time of the year, you're going to have different heat requirements and different heat rejection amounts. And really where solar thermal would come in is to make up any difference in these requirements. So where you would normally use a boiler, for example, you could maybe offset some of that using a solar thermal panel where they're going to produce warm water. And the important part here is I can't stress enough that it's warm water. It's not necessarily going to be hot. It's also going to really depend on outdoor conditions. So solar thermal panels work best, obviously, when it's summertime. It's going to be sunny, it's going to be nice outside, or it's going to be warm outside. And you're also simultaneously going to want to have a heat requirement in the building. So during the summertime, you're not going to be heating an ice rink. You're not going to have space heating loads, at least for the most part, as far as I understand. And that makes it a challenging sell because, at least in Canada, we don't have warm winters, and that's when you need the heat the most. So during the summertime, when you actually have this heat from the solar thermal collectors, you could use it to melt snow in a snow pit, or you can use it to produce, the domestic hot water. But for the most part, at least in an ice rink context, these systems don't really have that much of a place. Maybe you could use it if you were really required to preheat the resurfacing water, and you could somehow get higher temperatures that way. But while we haven't looked in detail at this point in time for this project, looking at using solar thermal collectors in an ice rink context, we don't currently anticipate them being a really strong candidate or being very economical to include. But maybe we're wrong. But nonetheless, I just wanted to point out that these systems, they work best when it's sunny, they work best when it's hot. But unfortunately, in an ice rink context, that's not when you need the heat. You need the heat when it's cold outside. And it really comes down to also just going back again is these systems that use heat recovery, that's really where you got to start looking first. And then you would use renewables to top up what you can't accomplish with heat recovery. That's the standard approach to getting to net zero energy is first reduce your loads, heat recovery, then renewables. So you got to make sure you're following that order, and heat recovery would come first. And then this is kind of, it just doesn't seem at this point in time to necessarily have a place. Yeah, so you can go to the next slide there, Catherine. And then this picture might not look like a ground source heat pump, but that's actually just a fairly old manifold. So a ground source heat pump, if you're not familiar, it's just like it's pretty much just a normal heat pump. But the important characteristic is you have a bunch of tubes that are buried in the ground. They can be buried horizontally, they can be buried vertically. If they're buried vertically, they're going several hundred meters into the ground usually. And what you end up doing is you're gonna put some fluid in the ground. If you put cold fluid in the ground, you'd have to put it, maybe at 2 degrees Celsius, you'd put it in the ground. It'll come back out, at least in Ontario, around 10 degrees Celsius. And that's what you would do during the winter time. So during the winter, you have a heating load in your building. So you're gonna start extracting heat from the ground, send water into the ground at 2, it comes back around 10. And that's good because now you have this 10-degree heat source that you can use combined with a heat pump. In the alternative situation, when it's summertime, you can supply, I don't know, maybe like 25-ish, maybe a little bit warmer than that, degree water to the ground. And then it's gonna come back out at 10 again. So pretty much all year long, because the thermal capacity of the ground is very high, you're gonna get this 10-degree heat source or heat sink that you can use from the ground, which then means you now not only have this very stable temperature, which can give you high COPs, you have your fluid being water instead of it being air that you would use over a condenser that's just an air chilled condenser. Or if you have an air source heat pump, you have minus 15 degrees Celsius air outside, and sometimes heat pumps can't even work that low. And really what you can look at this ground source heat pump, which is again unique because it's just a bunch of tubes buried in the ground that just allow you to have that 10 degrees Celsius water pretty much year round, is you can look at this as a long-term thermal storage. So during the summertime, when you have a cooling load in your building, you're going to take heat from your building and put it in the ground. During the wintertime, when you have a heating load in your building, you take heat out of the ground, put it in your building. The main benefit is that temperature should remain relatively constant as long as the system is balanced. So you want heat being added and heat being removed to be fairly balanced with each other. And then again, this is thermal storage, and this comes back to what we said before about any energy recovery. You want to make sure that during, let's say, the summertime, you have a bunch of cooling loads in your building. You can start filling the ground with some heat, such that during the winter time, when you have heating loads in your building, you can start pulling that heat back out. So there is an opportunity here, at least in ice rinks, that you can start making sure that on the annual basis, you're taking that heat that would otherwise be sent out using your chiller, or you'd have to be adding heat during the wintertime with a boiler. The ground source heat pump would allow you to save that heat and avoid using those auxiliary systems. But the main drawback that we're talking about here is these systems they're rather expensive to install. I did a quick back of the envelope calculation, and per ton of cooling, it was about $4,400 installed capacity per ton. We're finding, so I do some work in this field, we find that you can get payback periods if you have a well-designed system that are less than 10 years. But again, this is looking more in an institutional or maybe residential context. We haven't yet carried out the detailed calculations that are needed for an ice rink context. There is an existing system that does use ground source heat pumps in an ice rink context, but we haven't studied that in detail. And again, as Frank said, it's really in the details. When you look at heat recovery, when you look at these more energy efficient systems, you need to make sure that you're understanding the system as a whole, and this takes a little bit of time. And that's currently what we're working through right now. But we're not saying that ground source heat pumps are or are not a good idea at this point, but they are a candidate to potentially, on an annual basis, make your system more efficient. And as I said before, this thermal balance on the ground is also very important. There are many, we know of many schools that, you know, back in the early 90s, there was kind of a move to start putting ground source heat pump systems in, and it really turned people off because the systems just stopped working. They were, you know, they promised everything, and then they just wouldn't work anymore. They couldn't meet the heating demands. And those systems were designed to they weren't balanced. They were drawing a lot of heat out during the winter time and not putting much in during the summertime. And as I said before, if you're doing this, what ends up happening is that temperature of 10 degrees that you're getting out of the ground, it just starts going down year over year. And you need to make sure that these systems are balanced. So again, it's really is the devil is in the details here, and we need to be thoughtfully selecting which systems are economical to include. And it takes a bit of time just to make sure you go through the process to get a fairly good idea of what makes sense. Okay, so that's good for ground source heat pumps. So the next slide here. So just a couple other points. When you're looking at any of these systems, there are a few important factors. Number one, what's the peak load of the building? Number two, when you look at the design month of the building, and this is especially true for ground source heat pumps, the design month and looking at what your part load factor is. So just pretty much how much of the time is your equipment running during that coldest month of the year or warmest month of the year. And then on top of that, looking at the annual balance of heat over a year, you need to consider all three of these when you're sizing renewable energy equipment. And again, this is a little bit different than when you look at a chiller or a boiler. It's just, what's the peak load? Make sure it can meet that, and then you just know the amount of gas that you supply to the boiler. You can assume you have pretty much unlimited gas supply. It's going to come in from the city, and it'll be just fine. But when you look at these renewable energy systems, you actually need to consider not just the peak load, but the annual heat balances, the month. You need to consider all these things. So again, it just goes back to my point that it's important to understand. And as I said before, including the effects of energy recovery because of that energy balance is very important. And then as I think it was said by Frank and Jillian earlier too, it's just these trend logs. These are what allow you to understand how your system is performing and how you can design a system to take best advantage of the building that you have, your specific building with your specific climate and your specific schedules. It's important to understand these things. So starting these trend logs and saving them at 5-minute or hourly intervals and looking at the main heat and cooling energy consumers in your building, it's really important to start looking into that. And, you know, ice rinks, compared to many other buildings, they just have so much more complexity to them because there's this capability that you have something that requires cooling while the same component or a different component in the same building requires heating. And you really need to start balancing where the heat is being moved to as opposed to just paying to get new heat or reject heat from the building. Okay, that's all I've got. You can go to the next slide. And if you have any questions, feel free to post them there.
Jamie, there are a couple of questions in the chat box.
Yeah, I'm just reading that one now.
Yeah,
so I see
so let me,
James.
yeah, I could read them out for you if it makes it helpful.
No, I don't mind reading.
Okay.
Or yeah. So James Duff is asking, what type of foot squared is typical for a deep geothermal suitable for an ice rink? That's, again, as I said before, it's going to depend on the ice rink. It's going to depend on your schedules. It's going to depend, as I said on that other slide, it's the peak load, the monthly load during that peak month that leads up to the peak load, and then your annual energy balance. All of these are going to be systems building specific, and they're going to play into how large of a bore field you're going to need. So it's not a clear answer, but there are, if you knew the hourly demands that you would want this ground source heat pump to meet, you could go and calculate what the expected ground loop would be.
Right, with presumably why you want to also get your rink to be as efficient as it can be operationally now. So
correct.
Okay.
Yes.
Another question.
And again,
sorry,
this isn't just going to be the straight up heating and cooling loads of the building that you would input into this calculation. It's what you want the ground to meet. So if you have energy recovery where you take heat from your ice pad and use that to offset heating loads, then you know that the amount that the ground would need to make up for is going to be reduced. So again, it's really important to look at the overall energy balance of the system. And then from there, you can determine what the ground needs to do. And then you can go and size the ground. And the key here is you want to minimize that size of the ground. Because as I said before, it's about, I think I said $4,400 per ton. So these are expensive, but they're inexpensive to operate. So again, it's not the most straightforward answer, but hope that clarifies it a little bit.
There's a question too about if you've seen shallow geothermal design as opposed to deep geothermal design.
There are some. So there are some where you go shallow. Again, this is not in an ice rink context that I've seen it, but there are some situations where you're not going vertical, you're going with those horizontal boreholes. It's more of a slinky design. So there's just coils that are wrapped around horizontally, and it kind of looks like a slinky that someone just put on the ground and spread out. And then, it all depends on site conditions and what's available. But they do exist.
Okay, great.
So James had a follow-up comment, which he said, our rinks are fairly similar in design and energy consumption. So that's good. That means that once you go through the analysis for one rink, there would be only minor variation rink to rink, which would simplify the analysis once you get that first rink complete, but you still do need to go through the first rink. And no problem, James.
Great, thank you. So I don't see any open questions. We've set aside about 20 minutes for Q&A. So if you have any additional questions, now would be the time while we have our technical experts here ready and waiting to answer them. And I do see a question that's come up here. What are the good and bad if Simcoe refrigeration system is controlled by the whole building BAS system? Is that what the experts are recommending?
I can answer that one. So I'm just to clarify the question, when they're talking about Simcoe refrigeration system, I hope that you don't mean that the customer is tying within Simcoe for the BAS system. I think it's more open, saying that you need a control system, excuse me, for the refrigeration system, and you need a control system for the building. So we've done many projects and we have seen the good and the bad. So the bad that we have seen is when there's two different control systems. And just to give a very simple example, a refrigeration plant is running, building don't need heat, so the heat is dissipated outside, it's wasted. Refrigeration plant is not running, building is calling for heat, and again, it's like the boiler is going to start up because the two systems do not talk together. So I would say the best scenario is not necessarily a Simcoe BAS system, but it's a system which is handling both the refrigeration and the building. And both communicate, meaning that when the building is calling for heat, we need to run the plant. And if the building is not calling for heat, we don't need to run the plant. So basically, it's really having communication between both systems. So I hope I answered the question.
Yeah, Benoit, if I can add to that, it's a great answer. So far, based on our site walkthroughs, what we think currently will work best is that Simcoe's system can easily be integrated into the building automation system, which typically would read a lot of the good information that Simcoe's trend logging and monitoring. So currently the thinking is that again, Simcoe's so far the controller we think is a good controller that optimizes the more sophisticated operation of the refrigeration plant. But as Benoit said, is that a lot of that information can be communicated to the building automation system. So for the rest of the facility, that can again integrate it to say when heating is required, the refrigeration plant's doing the right thing to actually use that heat in the facility and vice versa, right? So that's kind of where we're thinking. Again, it's not a we don't envision a Simcoe for the whole Simcoe control system for the whole building. We envision an integration between them where typically a BAS system will just overlay and monitor the information from Simcoe and maybe give it some simple commands that Simcoe's controller or another refrigeration system controller can actually control the refrigeration plant, because a little bit more sophistication involved in that. Hope that helps.
So
Okay,
there's another question on what compressor improvements or efficiencies are being applied. So there's constant development from compressor manufacturer trying to improve their efficiency, but mechanical equipment is a mechanical equipment. So we're seeing slight improvement on piston compressor from some manufacturing being anywhere between 5 to 10% more efficient. There's a lot of development on screw compressor as well, but what we're going to see is not necessarily improving on the compressor itself, but it's reducing maintenance requirement and changing some of those parts, which could have a tremendous impact on the maintenance cost of the overall rink operation. The other thing that we see is on the heat exchanger, moving from some type of shell and tube equipment to plate and frame equipment, for example, where we can tighten the temperature difference between the operating fluid, whether it's ammonia with glycol, ammonia to brine, or CO2 to brine, or some stuff like that. When we're tightening those temperature difference, we are strongly improving the COP of the overall system. And this is what we're trying to achieve.
I think the next question from Stephen Hamilton looks like it's for me. Stephen asks, using rooftops for solar panels as a renewable offset. If not using a roof, how practical is a parking lot shelter to use as a renewable offset? It's going to depend on the available mounting area and then the orientation and the shading and the angle that you can mount the panel. So there's no real difference between a parking lot shelter or a rooftop. One good thing typically about a parking lot shelter compared to a rooftop is there's not a bunch of mechanical equipment that you also want to put there. So when you put a bunch of things on the roof of a building, you have exhaust penetrations that you need to start worrying about. You have structural loads within the building that you also need to start worrying about. You have the roof of the building itself that maybe it's really near the end of its life. So now you're forced to refurbish the roof and then install these, and it becomes more expensive. So there's a lot of practical considerations when you compare the two, but in terms of a generation perspective, if the area that's available is the same, if the shading factors are the same, if the orientation is the same, it wouldn't really make a difference.
So I can see that James have two questions. Are there companies other than Simco that can provide the controlling strategy? Of course, James, you know, any control company can look at the entire operation and provide a system that will take care of what's the requirement. And your second question is it better like recip compressor or screw compressor for ice rink refrigeration system? There's various approach to that. I would say it could be personal choices, but mechanically speaking, both of them will do the same thing. Piston compressor have a slightly lower energy consumption than a screw compressor, although piston compressor needs to have regular overhauls every 5,000, 10,000 hours, 15,000 hours, while screw compressors could run for 40,000 hours, 50,000 hours before overhaul. So if you compound those two factor into the equation, you know, energy consumption on one side and maintenance and overall, you know, cost on the other side, at the end of the day, I personally believe that the screw compressor is a better approach, especially that there's a lot of manufacturers which are actually building, I would say, light industrial compressor instead of the big heavy industrial machine that we see in industrial refrigeration. And also there's a lot of new development, and we can even start to see semi-hermetic ammonia compressor on the industry instead of having open ammonia compressors. So that would be a dramatically change into changing shaft seals and even the risk of having some ammonia leaks from the open drive compressors. So this is where the trend is going. This is where the market is going.
All right. I think Stephanie's question is for me, but it's pretty general. Given the long paybacks for these types of interventions, what approaches are being used to make these projects financially viable? On the whole, that's a very difficult question to answer, at least from my perspective. I think the first step is trying to figure out what the lowest hanging fruit is. As we said before, it's first, reduce loads, energy recovery, renewables. And you go through that list and you start to identify, you need to check the system. So we have, there's industry experience, for example, in this expert panel, that they've went and worked with a bunch of systems, and these systems have different performance levels, and you can try to develop on a subconscious or on a highly detailed statistical level, somewhere in between there even, you can start to get an understanding of which systems apply best in which situations. And then from there, you can start to use these to start guiding the analysis that you would then do in individual buildings and in different locations to start checking which ones are the most viable. Moving to a zero carbon future, it's still something that we still need to learn to understand, but it's an important step given the motivations based upon climate change that we need to reduce our impacts on the planet. And going through the process is just part of the journey that we are going to have to go through. Before there were boilers, they didn't know how to heat places. They were burning wood. It's the same concept that you need to start checking and using knowledge and trying to make the best decisions that you can based on the situation. So it's not exactly the most direct, like most of my answers, I guess. It's not the most direct or straightforward answer, but it's just, that's the process that has to be followed. It looks like Frank wants to say something.
Yeah, no, I wanted to talk more about, I guess it's probably Mario's question. It might be related to Stephanie's question, I guess. For Mario's question about when calculating payback, why is the capital cost of a component not factored in your calculations, especially given that the equipment is tending to fail before it's anticipated end of life? So there may be some miscommunication on my side, but we do, in the life cycle costing analysis that we will perform, we will be taking into consideration capital life. It was actually, you'll see in the last two slides of the heat pump analysis, it took the cost implications of going to a gas-fired boiler system as well as electric boiler. So the fact is, once a piece of equipment is either end of life or needs to be replaced, that is a trigger event. And so what are the options that you do with afterwards? So we'll look at all options, including capital cost and maintenance costs, as Benoit mentioned as well, in terms of the compressors, for instance. So you need to take maintenance into consideration. You need to take utility costs into consideration. But definitely capital costs will be a part of that, as well as, again, this, as Jamie mentioned too, this is kind of a bit of a newer territory for the approach that, based on the approaches that have been taken in the past. A lot of things have been focused on energy conservation, but now the low carbon approach is very different than just energy efficiency, because typically the approach for low carbon is to go to electrification, which costs a lot more than natural gas. At least today it does, anyways. And so that's sort of a different approach than typically energy conservation with the web. But that's real life. That's what we're up against. And in terms about financially making things financially viable, we're going to find out soon. We don't have all the answers. We're going to find out, which was kind of an interesting observation too, with the heat pump. The heat pump alone in itself is not a very very attractive financial option, but it's going to depend on a few factors. First of all, the capital cost of the heat pump or heat recovery chiller, as well as what's the price of carbon? What's the alternative to reaching the carbon goals? What's the alternative? And those will be explored a little bit further. Hopefully that helps out a little bit more. Oh, then there's another question, I guess, regarding some metering. Yes, so what we envision for the pilot, anyways, and is that we'll be doing, we're looking at monitoring, yes, the refrigeration plant in terms of energy uses. We're at this point in time, we're trying to get as much trend information as possible to facilitate getting energy usage. We will be adding likely CT sensors So to them, just to follow up, but not sure if that will be done for every single facility because of the implications of getting that done. But we're sort of at that stage now where we're trying to determine what we have in the trend log information, and then filling in that gap of trying to understand what the energy is used. If it can't be determined through the trend logs, we'll be looking at that for at least the archetypal facility, and maybe a handful of others where that is an important factor, a critical factor. Mm-hmm.
Okay, I can take the next question on CO2. Actually, what we're seeing on the market is actually not a pushback, but it's more interest into replacing system with CO2 system. So if I take an example in Quebec, 80% of the R22 system that has been replaced were with CO2 systems. So just to put things in perspective, nothing is perfect. No refrigerant has the perfect solution. So if we take synthetic refrigerant, they have a strong impact on the global warming potential, and they're not the right solution in terms of environment. If we take ammonia, it's a perfect refrigerant, it's natural refrigerant, no involvement in global warming and environmental issue, but it's a B2 refrigerant, meaning that it's toxic and it's flammable as well. So we need some construction on mechanical room that needs to take care of that aspect. When we move to CO2, it's an A1 refrigerant, meaning that it's non-toxic, non-flammable. It's comparable to R22, for example, but the only thing is we have to deal with higher pressure. So there's no requirement for heavier wall construction. Actually, CO2 systems are smaller in terms of size than ammonia system. We put everything that we can do to manage the safety issue regarding high pressure. So we're using high pressure stainless steel piping. Everything will be welded according to very specialized welding procedures. All the relief pipes are piped to the outside. And actually in Canada, because of the special nature of CO2, when we are using this type of system in the Canadian environment, we actually end up having a system with a better COP and with lower energy consumption. And again, it's an A1 refrigerant, so we don't even need a vestibule. In terms of if we ever have a release of CO2 into the mechanical room, this is the refrigerant that can have the highest concentration of refrigerant into the mechanical room. We're good all the way up to 50,000 ppm before affecting the health and the safety of the people inside. Any other refrigerant, any other synthetic is about 1,000 ppm. And when we're talking about ammonia, we're talking about 35 ppm. So that gives you an idea that CO2, yes, it does have higher pressure, but everything is put in place to make sure that this will not create a safety issue.
Ben, well, there might be a question about electric dehumidifiers too. Question: can a single dehumidifier generate the same amount of tons as a gas-fired desiccant?
Yeah, that's a pretty good question. The electric desiccants are available in smaller model, because at some point when we have higher, I would say bigger amphitheater, like I don't know, with 10,000 people, 15,000 people, the requirement in terms of dehumidifier will greatly steer toward using gas-fired desiccant instead of electrical. And it's only a question of what is the size of the electrical entry and what will be the requirement of amperage and stuff like that. So they are available in smaller size. In some gap, we have both available, gas-fired and electrical. And when we get into the bigger size, it will be gas-fired desiccant. So there's another question on CO2 system. Yes, CO2 system does use higher pressure than ammonia. So typically on the low side, we will be around 400 PSI, and on the high side, we will be around 1200 PSI. So And an ammonia system will be about 30 to 40 PSI on the low side and maybe all the way up to 200 PSI on the high side.
Okay, it looks like we don't have any open questions left. I guess we maybe got one more minute if anyone has a last minute question they want to throw in there. Okay. And I don't see any in the chat box either. So that's great. Well, thank you everyone for your questions and your answers. I think everybody learned quite a lot. I know it was a lot of technical details, but hopefully slowly everyone's coming up to speed with that. Okay, so I think we're ready to move on to sort of the implementation piece and getting ready organizationally. So Jillian, I'll hand this back over to you.
Thanks very much, Catherine. We touched on this in last year in our forum, so I think it'll be very interesting to connect with our member municipalities and others to see where they are in terms of some of this getting ready for net zero. We spoke a little bit about this at the beginning, but wanted to touch on these. Again, this is sort of best practices that we've gleaned around getting ready for projects. The idea of having criteria and data to identify key projects that further your climate goals, as well as renew your infrastructure, make sure you're meeting your service requirements, and ideally saving money, which, you know, balancing all of those things is your juggling act for sure. You want to be able to have this list, this prioritized list, and give yourself the runway to do it. Doing things differently is going to take time. So being able to have a runway where you have time to be able to gather your experts and have this time is key. The low carbon design brief, we spoke about this in detail earlier. We do have municipalities working on this right now, and this end vision for each facility is going to be key in developing the capital plans and your look going forward. The feasibility study, having our business case, we're going to need to have the business case, least cost approach, taking life cycle into account, and that's certainly something to start working on now. Having your integrated design team, the right people and the right processes at every stage, getting all the players at the table, starting to collect your players now, outside, inside those ones. That's all part of the plan, and design and operational standards. Making sure, figuring out your best practices for design in your municipality and how to run the buildings from experts, from others. Certainly what's something we're hoping to help you with through this process. And one of the things coming out of the pilot will be to help you both with design and with operations in terms of standards. Thanks, Catherine. You can move on to the next one. In terms of organizational best practices, once again, getting your capital planning over multiple years, getting those prioritized, prioritizing your least carbon projects, absolutely key. Organizational alignment, we talk about this all the time, but getting people on board with the idea, aligning what you consider important for your municipality or what your municipality considers important with your carbon goals. So activities to align with carbon goals, how you make decisions, what you're talking about, what you're measuring, all of those should be aligned around the carbon goals. Asset management, this is getting your emissions and utility cost savings and your carbon goals embedded in the asset planning. We're going to be very lucky to have some experts on November 18th in our next segment of our forum speaking specifically to this. So I won't touch on this very much, but that'll be a very interesting discussion as to how municipalities are changing how they look at planning their assets. Procurement, developing policies and processes so that least carbon products and services will be procured. We've had some discussion today about the challenge of when something is not necessarily, when your option for lower carbon is not necessarily the lowest cost up front, and how we're going to defray that. That's going to be an ongoing challenge, and figuring that together is definitely going to be a priority. Reporting and communication, spreading the word, reporting on how you're doing, keeping track of how you're doing, and reporting it to others. A number of our member municipalities are already doing this, and we have some great webinars on our website where they discuss how that's happening. They're sharing their building performance reports with their operators, communicating how they're doing against environmental goals. All those things are happening, but ratcheting it up to the carbon goals as well. And staff development and what does staff need to know? Is there training that needs to be done? Thinking that through, and what do we need to start telling people in our buildings? So that's another piece to think about around organization. Next. So this was the feedback we got from last forum, where we, as Catherine mentioned, our program is based on member-driven content and what members are interested in. This is what the members were fed back to us, so their priorities last year. We're interested to hear from you if these are still your priorities, but their priorities were organizational alignment, capital planning and procurement, design and operation standards, those three things. Getting changes in procurement processes was a theme. Well-developed business plans with life cycle analysis, teams, better communication, that's all piece of it, and expert knowledge. So tapping into expert knowledge, and we've been working on that for this pilot and hope to continue to bring this to you. And last but not least, implementation support and scaling up. As you've heard from Frank and others, we are working away at the technical component of the ice rink pilot. And the next phase after we get through that will be supporting the implementation. As many of you know, the greatest plans can be developed, but if you don't have support, then they don't always get implemented. So that's key for us. Procurement support, how we can help around RFP language, scopes of work, etc. Developing a life cycle costing tool that will look at these measures and help you with life cycle costs, which will have measure costs, those kinds of things. For rule of thumb, obviously it won't be necessarily specific to your building, but will help you with at least developing the business case and planning for the future as you do your capital plan. Design and operation standards, the sharing lessons learned, I think is going to be a big piece. The cohort approach, learning from each other, that's going to be key. And then as part of scaling up, the lessons learned from this will be shared, and we will be documenting the process the process to get here. So how we got to this net zero design for these rinks and how we got there, that'll all be shared. I believe I was going to turn it over to Catherine, but I believe there's a question about who's working on the arena project. Absolutely. Yeah, we can share that back to you, Gabriel. We'll do that offline. Were there any other questions? Sorry. Oh. General template for a low carbon design brief. Great question. We have, we certainly we will have at our next session on November 18th, we have one of our member municipalities, the town of Halton Hills, is actually putting together a low carbon design brief. So they can talk to the specification they put out to that and how it's working for them. So if you have questions, I would highly, highly recommend you come to that session on November 18th, because they can answer all the questions around how that's actually working out in live and in person, and specifically for them. Okay, any other questions? Okay, I'm going to hand this over to Catherine. Do you want to take it away?
Great, thank you, Jillian. I think that was really helpful for everybody. So for our members, they will know all this, of course, but we have quite a few folks on the line who aren't necessarily familiar with everything we do with the mayors. So I won't take too much time on this, because you can always contact me and we can have further discussions about it. But the 4 pillars really of the MMC program are energy management, knowledge, networking, and recognition. So on the energy management side, all of our member municipalities receive an energy savings and opportunities report for each of the buildings enrolled in the program. And this highlights opportunities where the savings can be found in the buildings. And I'll share in a few minutes the methodology that we have that explains how we come up with this savings potential, but it points to specific areas in the buildings where there's opportunities for savings. And our members often share these with energy auditors, for example, who are then tasked with finding these savings that are there. And members also share the reports with their building managers and operators as a means to engage them and point to the savings they've already achieved and additional areas of opportunity. So they're a great engagement tool. In terms of knowledge, so we provide tools. We actually had for the Town Hall Challenge, an electric mini audit that the members were able to use this tool to pinpoint areas where energy use was high, such as lighting or HVAC. And then they were able to use that to achieve the target of 20 equivalent kilowatt hours per square foot. And many of our members were able to do that. And in terms of other tools, we're currently developing the life cycle costing tool that's mentioned a few times through the pilot to help municipalities make the financial case for net zero improvements. Recognition is huge. So members receive awards for making savings and achieving targets, which we'll be presenting our awards shortly. The awards have been really useful for members in terms of engaging senior management, council, and the public on the energy initiatives and improvements that they're making in the municipality. And peer networking is probably one of the strongest components of the program. It's mostly done through webinars and a way for the energy managers to connect with each other, as well as connect their facility managers and operators with others. And we found, particularly over this past year, that the operators really like talking to each other and really can learn a lot from what other operators are doing. So we're going to continue down that path. It's becoming very valuable for people. So all of this to say, I guess the two fundamental components of the program are also results supported by data and the sharing of knowledge and best practice that I mentioned, which is done through webinars. And I get questioned very often about how our webinars are different. So member-driven content is probably one of them. So we really choose our topics on things that are of priority to our members, things that they've asked about, things that they want to hear about. And again, supported by real data. So if we have any case studies, that's supported and backed up by the data in our green building performance system to show that those savings are actually real. And they're meant not just to be informational, but structured to lead to action. And really highlighting issues and challenges experienced on the ground by real operators and real building managers to learn from what they've experienced and really take their lessons learned and apply them going forward. So really taking that collective approach. Okay, so just to get into a little bit of how we determine where these savings opportunities are to be found. And it really starts with benchmarking. That's the first step. So benchmarking your buildings against our database of similar buildings. This can include admin buildings, community centers with or without rinks and pools, fire stations, libraries, pretty much any municipal building type in the municipality. But of course, we then take that a step further because it's really simple benchmarking isn't really an apples to apples comparison because the buildings are so different from each other. So the first step in there is breaking it down by energy use component. So we break down the benchmarking into electric baseload, cooling, and heating. And the targets come from the top quartile of that data set. And then similarly for thermal, benchmark the gas baseload and the gas heating. And then the target becomes the top quartile. But again, simple benchmarking doesn't work. You really need to make an apples to apples comparison. And that's where the adjustments come in. Oh, and before I move on to those adjustments, so these are the targets for different municipal building types in each of those different components. And these are the base targets, and I'll get into the adjustments because of course you'll need to adjust for things that make the facilities individual or specific, and weather would be one of these things. So this comes back to the apples and apples comparisons and the adjustments. So we adjust the targets for material things in the buildings that make them different, For example, data centers or other energy intensive equipment, or in the case of ice rinks, the number of ice pads and the months of ice in are all differences in the building that need to be adjusted for. So we have a couple of white papers that are up on our website that document all of the methodology, how we determine the targets, and these have been peer reviewed by municipal energy and industry leaders. So please feel free to visit our website if you're interested in how we determine the targets and savings potential for the different building types. And this is sort of an example using 5 fire stations from a municipality and showing the actual energy use, the adjusted targets. So you can see that Fire Station 6 has a different electric baseload target than Fire Station 1, and the different savings potential in the areas for each of these different fire stations. And there's points of interest, of course. One of Fire Station 1 has much higher electric heating than the others, and so on. And really the whole point is to really, for our portfolio level, show you where to look for your savings. So this table highlights where the opportunities can be found and where to look for the savings. So if your energy use is higher than the target in electric baseload, you would look to your lighting, fans, pumps, ice plant. If your electric cooling energy use is much higher than target, you'd look to your air conditioning, for example. So it kind of gives a high level overview of where your different buildings are sitting. And again, if you have any questions about this, I have a deeper presentation that I'd be willing to meet with you and go over about if you have any questions on that. And that being said, we are on to our awards. So this is a photo from our forum last year, and we had quite a few of our members receiving awards. And this year we've actually had such a high number that we've had to split them up into 2 days. So today will be the savings awards for buildings that have achieved over 10% savings in 2019 versus the prior year, 2018. And on day 2 of the forum, November 18th, we will present the leadership awards for high performing buildings that have reached their targets or exceeded their targets. So today is the 10% savings awards. And we'll start with the City of Richmond Hill. They have received 3 awards this year for achieving over 10%. And interestingly, they're all for their pools. So the Lois Hansey Aquatic Center, Centennial Pool, and Bayview Hill Community Center and Pool. So first, Lois Hansey was close to almost 20% total energy savings and greenhouse gas emission reductions of almost 117 tons, which is fantastic. Centennial Pool over 14% savings and 41 tons. And Bayview Hill is 10% savings and 61 tons. So fantastic savings in these 3 facilities. And I really see an awesome case study next year, City of Richmond Hill, if you'd be willing to share with the members some of the measures that you've done in these pools and how you were able to achieve the savings, and maybe share some of those tidbits with our other members so they can work to get there as well, because of course there's a lot of savings to be had in these large pool facilities. So congratulations to the City of Richmond Hill, and we will be mailing your award to you at some point shortly. Okay, congratulations again. So next, the Township of King, and 2 awards for the Township of King, and again for fire halls. So Schaumburg Fire Hall with almost 13% total energy savings and 5 tons of greenhouse gas reductions, and Nobleton Fire Hall with over 11% savings and almost 4 tons of greenhouse gas reduction. So again, another opportunity for a case study next year, I think, since they're both fire halls, and maybe sharing again with the members what was done in these fire halls and how it could be shared with others in the program. So congratulations to the Township of King. And next, the City of Mississauga and 2 community centers, Frank McKechnie Community Center and Carmen Corbassin Community Center, both with just over 10% total energy savings and fairly large greenhouse gas emission reductions of 45 tons and 54 tons. Again, another awesome opportunity for a case study for Mississauga to share with others what was done in these facilities to achieve these savings. And City of Barrie. So an award for East Bayfield Community Center, which is a multiple award winner, has won in previous years. So they continue to make savings year upon year, which is fantastic. Total energy savings of 17% and 148 tons of greenhouse gas emissions. And an award for Barrie City Hall at 10% savings. So congratulations to the City of Barrie. And Town of Halton Hills, 10%, actually almost 14% savings, total energy savings for another fire station. So maybe they could share some of their, some of the measures they employed as well, and can join the Township of King in sharing that with others. Most of our members have multiple fire stations, so there's lots of opportunities here. So congratulations to the Town of Halton Hills. And last but not least, the Town of Caledon, who actually, they presented this case study at our forum last year on the many measures that they've undertaken at that facility, and an impressive total energy savings of almost 33% and greenhouse gas emission reductions of 27 tons, almost 27 tons. So congratulations again to all of our award winners, and they will be, the physical awards will be mailed to you. And again, our leadership awards will be presented at the day 2 of the forum on November 18th. And I think I have a question coming up here. Oh, no, okay. So moving on. So today, of course, was day 1 of our forum, and the next is coming up on November 18th. And the time is the same, 9 a.m. till 11:30 a.m. And we have a number of municipalities coming to present how they are integrating climate reduction goals into their municipal energy management systems. So hope you can join us for that one. And day 3 is on Wednesday, November 25th, again, 9 a.m. and looking at different financing pathways, because of course, financing has always been listed as one of the main challenges of getting things done. So we're going to address a number of different financing mechanisms that municipalities have used to fund their projects. And there's some registration information below if you have not yet registered, or please get in touch with me if you would like to figure out how to register if you haven't been receiving the newsletters. And I guess now would be a time that we could answer some more questions. We finished a few minutes early here. So if you have any more questions, please feel free to enter them into the chat box or the Q&A. And otherwise, thank you so much for joining us today, everyone. I hope you learned a lot, and we look forward to seeing you, or at least hearing from you, on November 18th. And we will stay on the line till 11:30 to answer any questions.
Thanks, everybody.
Thank you, Raji. I see your thank you in the Q&A. Thank you very much. Please get in touch if you have any other questions. Oh, and lots of thank yous in the chat box. Thanks so much, everybody. I'm glad you enjoyed it. And again, we will post the presentation up on our website, and we'll circulate, and we'll have a forum proceedings and Q&A document circulating after as well.